Okay, guys, let's start. Any questions regarding the previous topics? Okay, let's continue with the arithmetic properties of limits of a sequence. Почему красный? Не нравится красный. Definition. A sequence xn is called infinitely small if its limit is 0. If we wrote down this definition, it means for any epsilon greater than 0, there exists capital N, such that for any n greater than capital N, it follows xn minus 0, absolute value less than epsilon. Note, a sequence xn having a limit of a is the same as sequence xn minus a having a limit of 0, which is, as we just defined, means xn minus a is infinitely small. This first part is very easy to prove just by writing the definition. Let's write the definition of this limit being a and write definition of this limit being 0. And we will see that we have the same statement. It will be this statement, and at the end it would have xn minus a, absolute value less than epsilon in the first case, and minus 0 in the second case. You can write it down and see. Very easy. Very easy. Lemma 1. Let xn and yn be infinitely small sequences. Then, if we add them or subtract them, we will also have an infinitely small sequence. Proof. So let's write down the definition of sequence xn being infinitely small. Limit of xn equals 0 means for every epsilon greater than 0 there exists capital N, I will call it N1, natural number, such that for any n greater than n, it follows that xn minus 0 absolute value less than epsilon by 2. Look, I have written here the definition of the limit of this sequence, except this little bit at the end. I have written here epsilon divided by 2 instead of epsilon. Let me explain how is this correct. Look, for any positive epsilon, there exists a capital N and so on. And if you give me any positive epsilon, I can take half of this number. This will also be a positive number. I will find capital N corresponding to this half of epsilon, and then I will have this inequality. So I can just for a given epsilon find any number capital N such as this is correct. This basically means that I can multiply epsilon over here. Instead of epsilon, I can write down epsilon multiplied by any specific positive number. Can you see? I can write it either 1/2 or maybe times 2 or any other positive number. I cannot, of course, multiply by 0, negative number. And very important part, this number that I'm multiplying should be some constant number. It shouldn't depend on other objects in this definition. But in any case, this is still correct, and we will use this trick a lot in the future. Okay, so this is the definition of limit of xn being 0. So xn is an infinitely small sequence. Okay, now let's write down definition of limit of yn being 0. Greater than 0, there exists n2 for n greater than n2. It follows that yn minus 0 less than epsilon by 2. I of course write here minus 0 just for the sake of strictly following the definition. This of course means just xn and yn. Okay, very well, very well. Now, so for any epsilon this is true, for any epsilon this is true. This means that for any epsilon there exists a number capital N that I will take as maximum of n1 and n2. Such that for any n small greater than capital N, look, since capital N is maximum of those two numbers, from small n being greater than capital N, it would follow that both those statements hold. Can you see those inequalities? Okay, so both of those statements hold. It would follow that absolute value of xn less than epsilon divided by 2 and absolute value of yn less than epsilon divided by 2. But from here it would follow that absolute value of xn plus yn being less or equal than absolute value of xn plus absolute value of yn is less than epsilon divided by 2 plus epsilon divided by 2, which is just epsilon. So, for any epsilon, I found a number capital N such that starting from this number, elements of sequence xn plus yn less absolute value, less than epsilon. This, of course, means that the limit of xn plus yn equals 0. Tends to infinity. Which means that this sequence is infinitely small. Also, if I have a sequence xn minus yn, I can just put minus over here instead of plus. I can put over here minus, and all of the rest of the proof is the same. So a sequence xn minus yn is also infinitely small. End of proof. Theorem 1. Let sequence xn have a limit a, real number, sequence yn tends to b. Then there exists a limit xn plus yn, which is a plus b. Proof. We can see that expression xn minus plus yn brackets minus a plus b is the same as xn minus a plus yn minus b. This is just an identity. By virtue of this note that I wrote over here, that limit of xn being a is the same as xn minus a being infinitely small, of note. Maybe I'll call it note 1. Let's call it note 1. Sequence xn minus a and yn minus b are infinitely small. By virtue of Lemma 1, using this identity, we just see that this sequence xn plus yn minus a plus b, this sequence, is just the sum of those two sequences. Sequence xn plus yn minus a plus b is infinitely small. And once again, by virtue of note 1, this means that this sequence tends to a plus b. There exists limit tends to infinity, xn minus yn equals a plus b. End of proof. Questions? Lemma 2. Yeah. Plus, of course, plus. That was a typo. Of course, plus. Let xn be an infinitely small sequence. And yn be bounded. Then, if we multiply them, we will have an infinitely small sequence. Xn times yn is infinitely small. Proof. sequence yn is bounded, means that there exists a number, capital M, real number, such that for any n yn absolute value less than capital M. This is just the definition. Xn is infinitely small, means that for any epsilon greater than 0, there exists a number n such that for any small n greater than the capital N, it follows that xn absolute value less than epsilon divided by capital M. Here I'm using this trick once again. I am multiplying this number. Instead of epsilon, I have epsilon divided by M. Since number M is obviously positive, look, this is a positive number, then this is also a positive number, and we can see, of course, that this number does not depend on any of other entities in this line. It's just some number regarding the other sequence. Okay, but this would mean, but from here it would follow, then xn times yn absolute value would be, I'm multiplying this inequality and that inequality, would be less than epsilon divided by m times m, which is just epsilon.
I didn't quite get the statement about xn modulus is less than epsilon divided by m.
Okay, I think this was because you didn't hear the first explanation. Let me repeat it. Okay, let me do this in a second. Okay, so for any epsilon, there exists capital N such that for any small n greater than capital N, xn times yn absolute value less than epsilon, which means that xn times yn is infinitely small. End of proof. Now, let me repeat this explanation. For any positive epsilon, there exists capital N and so on, definition of the limit. Now, since this capital N exists for any positive epsilon, if you give me some positive number of epsilon, I can multiply it in my mind by some positive number, any specific positive number, for example, by 1 divided by capital M, and find this capital N corresponding to the result of this multiplication. Correct? So, for any positive epsilon that you give me, I can find capital N such that for any n small n greater than capital N, this holds. Correct? And this would work for any specific positive number that I know as a coefficient over here. So yeah, we'll use this trick. a bit. Okay, any questions? Okay, moving on. Theorem 2. Let xn tend to A, yn tend to B. Then there exists limit xn times yn, which is A times B. Proof. Once again, we can say that xn minus A is infinitely small, yn minus B is infinitely small, and let's consider a sequence xn times yn minus A times B. Actually, let me write it all of it down. Xn minus A and yn minus B are infinitely small. Okay, at the end I will prove that a sequence xn times yn minus A times B is infinitely small. This is my goal. Okay. Let's consider just this expression xn times yn minus A times B. I am adding and subtracting xn times b. I'm writing down xn times yn minus xn times b plus xn times b minus a times b. I have added and subtracted this term. Да, и что? Нормально. Okay, but now let's put brackets like that and take common factors from those brackets. This would be xn times yn minus b plus b times xn minus a. Now, since yn minus b is infinitely small, and xn is, let me write it down. Xn is convergent, hence xn is bounded. We proved this theorem, I think last time. From here, it follows that this first term, we are multiplying a bounded sequence times infinitely small sequence. Xn times yn minus b is infinitely small. Also, we can consider this number b a constant sequence. So this is a sequence that just repeats the same number. B, 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 and so on. So here we can also see that this is a bounded sequence times infinitely small sequence. Similarly. B times xn minus a is infinitely small. Okay, let me expressly write down that this is by Lemma 2. Okay, then this expression is the sum of two infinitely small sequences. Then by Lemma 1, xn times yn minus I times b is infinitely small. Hence, by the note 1, there exists a limit of xn times yn equals a times b. End of proof. Exercise. I think you can prove it yourself. In my group, we discussed it on the seminars, but the other group can just think about this a bit. It's simple enough. Theorem 3. What's going on with this block? Let sequence xn have a limit a, then there exists a limit of xn absolute value, which is absolute value of a. Proof. Let's write down this definition. Absolute value of xn minus a less than epsilon. Then, by virtue of this exercise, absolute value of xn absolute value minus a absolute value is less, actually, or equal, less or equal. I'm sorry, guys, fixing your notes, less or equal. Absolute value xn minus a, which is less than epsilon. From here, this is just by definition, for any epsilon, I have capital N, that for any smaller and greater than capital N, this expression less than epsilon. This, by definition, means this limit. Okay, let's take a break, 5 minutes break. Okay, let's continue. So I have made a mistake over here, and only one person noticed. But anyway, let me redo this part. This, of course, was a true statement, but not useful over here. Here I needed another statement. Instead of that, I wanted to have x minus y absolute value. This statement, a different exercise. This is what I need here. Look over here, xn minus a. Okay, sorry about this mistake. Okay, let's move on. Lemma 3. Let xn converge to a number a such as a is not 0. Well, a is a real number, but not 0. Let also for any n, xn not be 0, also not 0. Then a sequence 1 over xn is bounded. Proof. By Theorem 3, absolute value of xn tends to absolute value of a, which is not 0. Actually, I don't need this not being 0 right now. Let's write down this definition. And here in this definition, let's take epsilon equals absolute value of a divided by 2. This is a positive number. Since a is not 0, then this is a positive number. This statement says that xn absolute value is less than absolute value of a plus epsilon and greater than absolute value of a minus epsilon. This statement says that, which means, in particular, so I am taking epsilon equals this value and I'm looking at this part of inequality, this part. This means absolute value of a divided by 2 less than absolute value of xn. And from here it would follow that 1 over xn absolute value is less than absolute value of 2 divided by a. Okay, so starting at some point, starting here, all of the terms of my sequence 1 over xn are smaller than this value. Absolute value is smaller. Let's take all of the previous terms of my sequence. 1 over x1, 1 over x2, and so on. 1 over x capital N. And let's take this value 2 divided by a, and let's take absolute values of all of those values, and let's take maximum of all of those values. Let's call this value m, capital M. For any natural n, I'm going to say that 1 over xn absolute value is less than capital M. Indeed, if small n is greater than capital N, yes? Less or equal. Thank you very much. If small n is greater than capital N, by the virtue of these inequalities, I have, and also m being not less than 2 divided by a, I have this statement. Very well. And if small n is smaller or equal than capital N, then by virtue of this number capital M being maximum of those, I also have this inequality. So this holds for any natural n. End of proof. Okay, questions? Theorem number 4.
Since we already proved that 2 by absolute value of 2 by a is greater than all the numbers in the sequence, then what was the need of taking another constant m?
Yes, this is a good question. It seems that we already have a constant that is greater than the terms of our sequence 1 over xn. Why did I feel that I needed to write more lines over here? Why didn't I just finish it there? Who can answer? Okay, because this is true not for all of the terms of my sequence. This is true starting at this point. Can you see? So the first terms of my sequence could be any other number. You can easily see that this number 2 divided by a depends only on the limit of the sequence. And the limit of the sequence would stay the same if you change several of the first terms in any way you want. Yeah? So, for example, you can set the first term x1 as being a specific number you want. For example, exceeding this limitation. Okay, theorem 4. Let xn tend to a, yn tend to b, also b not 0, and also yn not 0 for any n. Then there exists a limit of xn divided by yn, which is a divided by b. By the way, in this theorem and in the previous lemma, this condition that those are not 0 is just a technical condition because I'm dividing by those numbers. Can you see? So I'm just escaping this problem with the division by 0. Generally speaking, b couldn't be 0 because I still have to divide by b over here. But if some terms of y, for example, are 0, this sequence xn divided by yn, while not defined at some terms, will still tend to infinity. So, for example, if y, I don't know, y5 is 0, then this sequence is not defined at number 5. But if we redefine it in any way at this problematic point, this sequence will tend to this number. I'm not going to go there and discuss this. You can easily see that this is true yourself. I'm proving this formulated like this. Proof. So once again, I'm considering an expression xn divided by yn minus a divided by b. I want to prove that this is an infinitely small sequence. I will write it down like that. That would be xn times b minus yn times a divided by yn times b. I will add and subtract in the numerator a times b. And I will write the denominator as a factor. I will write like this: 1 over yn times 1 over b times xn times b minus a times b plus a times b minus yn times a. And I don't need to divide it. Let me erase this. Times that equals 1 over yn times 1 over b times xn minus a times b plus a times b minus yn. And once again, this expression is, let me, different color. This is infinitely small sequence. If we multiply by a constant, as we discussed, it would also be infinitely small. So this is also infinitely small. The same happens here. This is infinitely small, b minus yn. And if multiplied by a constant, also will be infinitely small. So this big bracket contains a sum of two infinitely small sequences, which means this is also infinitely small. All of this is also infinitely small. This sequence, y over 1 over yn, is bounded by virtue of Lemma Three. Let me write it down. And 1 over b is just a constant, also a bounded sequence. Also bounded. Okay, bounded. So we have a bounded sequence times infinitely small sequence. This is also infinitely small sequence. Hence, the sequence xn divided by yn tends to a divided by b. End of proof. Any questions? Any questions? So, those were the theorems regarding arithmetic properties of limits of sequences. Our next topic is the Kashi criteria. Definition. A sequence xn is called a fundamental sequence or Kashi sequence if this next condition satisfies. If it satisfies this next condition. For any epsilon, there exists capital N such that for any number n greater than capital N and also any number m greater than capital N, it follows xn minus xm less than epsilon. There is also an alternative way to write this down. Look, let me write in brackets. An alternative way. For any epsilon, there exists capital N such that, look, here I have two numbers greater than capital N. If small n equals small m, then this expression is just 0 and is automatically less than epsilon. So this is not an interesting part. If otherwise one of those numbers is greater than the other. So let's call it the smaller of those numbers n. Let's consider n the smaller number. I will write it down once again. Then capital N. And the difference between those numbers, that is m minus n, is a natural number that we will call p. And for any p natural number, it follows xn is the same and xm, m is just n plus p. So I'm writing minus xn plus p, absolute value less than epsilon. So this is just the same statement written a bit differently. Theorem, very important theorem. It's called Kashi's Convergence Criterion. A numerical sequence converges if and only if it is fundamental. Proof. So I have to prove two statements here. If a sequence is convergent, then this sequence is fundamental. And the second statement, if the sequence is fundamental, it is convergent. So let's start with the first proof. Let there be a limit of a sequence xn equals a. I want to prove, then from this statement follows that xn is fundamental. Okay, let me write down this definition of this limit. For any epsilon greater than 0, there exists capital N. For any n greater than capital N, it follows. And once again, I'm using this trick. Xn minus a less than epsilon divided by 2. Now, I have written this statement, and here I used letter small n. I can also write again this same statement, but over here just write down a different letter. This is just a name of the number of our element of my sequence. So nothing changes if I change the name. So over here, I can also write that for any m greater than capital N, it also follows that xm minus a less than epsilon by 2. Then we have absolute value of xn minus xm. So terms in this first and second line are generally speaking different terms. Let's consider them. xn minus xm is of course absolute value of xn minus a plus a minus xm, which is of course, I will put brackets like that over here, and here we have an absolute value of a sum. It is less or equal than the sum of absolute values. Then absolute value of xn minus a plus absolute value of xm minus a. Which, as we have written above, is less than epsilon divided by 2 plus epsilon divided by 2, which is just epsilon. So, for any epsilon, there exists capital N natural, such that for any n and m greater than capital N, it follows that xn minus xm less than epsilon. That means xn is fundamental. Sequence is fundamental. Why are you taking pictures of the board? Are you not writing this down? You are writing this down. Why do you need? You don't? But please do. This is important to understand. This. Now, so I have proven one half of this theorem. I have proven that if a sequence converges, then it is fundamental. Now let's prove the other way around. Now, let xn be fundamental and I want to prove that it is convergent. So the sequence is fundamental, so for any epsilon greater than 0 there exists capital N, so that for any n and m greater than n, it follows that xn minus xm less than epsilon. Actually, let's put here epsilon divided by 3. Epsilon divided by 3. So I can rewrite this expression as follows. xn is less than xm plus epsilon divided by 3 greater than xm minus epsilon divided by 3. So, if I fixed number m, then this number on the left side and this number on the right side are some fixed numbers. They do not depend on n. So this means that all of the terms of my sequence starting from capital N lay in this interval. And since there is only a finite number of terms of my sequence that have smaller numbers than capital N, then my whole sequence is bounded. Let me write it down. Fixing M, natural, we find that for any n greater than capital N, it follows xn minus epsilon naught xn plus what's the best way? Whatever. Let's call capital M maximum of x m plus epsilon xn m1 I'll write it down. There exists this number. Look, I'm taking a maximum of all of the terms with smaller indices than n, and this number xm plus epsilon divided by 3. This is a finite number of numbers, so there exists a maximum of those numbers. Okay, and it would follow that for any natural n, xn is smaller than number m1. Can you see? Similarly, there exists a number m2 that is a minimum of xn such that for any xn is greater than m2. Hence, a sequence xn is bounded. Okay, I have proven that this sequence is bounded, but I haven't proven the last step. I don't have enough time for this right now. I will finish it next time. And right now, we still have 1 minute, and I will ask you to do a very small test. So, all of you, including the people that are watching through Zoom, will solve this next problem. Take a picture of your solution, or just write down the solution in email and send me by email. You have, well, until the next class starts, so 11 minutes. Basically, you need 1 minute to solve it. Whatever, let me give you a test. Let a sequence xn be convergent prove that a sequence xn squared is also convergent. So, very small test, solve it and send me by email. Thank you for your time, thank you for your attention. If you have any questions, please ask away. Any questions? If you don't have any questions, then goodbye.